So our next, gentlemen and ladies, we have just finished this in the part one, finished designing the sewer network. So the next thing we're going to do now is to design the stormwater network. So if this same drawing has been given to you and you are asked to design the stormwater network, what do? The first thing you do, as we said, is that you write down you bring it down in this way. What is the catchment area and what is its length, what is the slope, and so on and so forth. Okay, you now create a chart like this. That chart you're going to create will have the catchment, the beginning, the end, the area. Then you ignore these two because this two is for the sewer. You now start from the peak runoff. This is the peak runoff. So in designing the sewer now, what do you do now? This you make the assumption is that we're looking at a rain of 126. Let's say it's Abuja, 126 liters per hectare. Okay, and we're looking at a rainfall duration of 10 minutes. It can be also be 15 minutes. Okay, good. And we are looking at 5 years return period. Okay, I've discussed this before. And that's the equivalent of frequency of 0.2 because it's 1/5. It's 1 over return period. Frequency is n is equal to 1 divided by a. Okay, now 37% runoff coefficient. That's what we use. How did we arrive at 37%? We looked at what is the area that is full of grasses, what area is streets, what area is roof, what area is other things unaccounted for. We took their respective peak runoff and now calculated the average of it. Now gave us this. So this is the formula we're going to be using. Rainfall intensity times the area of impervious area, which if broken down will mean rainfall intensity, which is a function of duration and frequency, multiplied by the peak runoff. Okay, so now, if we are not calculating for runoff now, we assume all these values. For catchment A, the area is this. Therefore, the runoff now, which is QR, I don't know how to put that, but that is Q, capital Q. Oh, I can do this. This is word underscore R. Okay, this is possible here now. Yeah, this is it. So this is runoff. Or sometimes flow. So the flow now is 126. Remember the formula for the flow. The formula is QR time multiplied by the rainfall intensity multiplied by, I don't know how to get this formula, but I know this is word. I can get it. Insert symbol. That will take too much time, but it's not undoable. What currency are we looking at? Special characters? No. Well, now let me not waste our time. But I'm just looking for the. Let me just use this one. Yuan. Whatever. Okay. Multiply by this. Okay. Which means rain intensity multiply by the area multiply by the peak coefficient. I don't think that's the expression of coefficient. So I don't know if that's the expression of coefficient. So look at it now. So Q equals to flow equals to this and equals to A. Good. This is what it looks like. So here we say, so that becomes 126 multiply, that's the runoff, the rainfall intensity, multiply by the area. The area for catchment A is 15.63, multiply by the runoff, peak runoff coefficient is 0.37. Okay, and the whole runoff coefficient is the same. So what will be changing will just be the area for each. Gentlemen, I want you to imagine this: somebody that have a small compound and somebody that have a big compound cannot have the same water coming out from the catchment. So it's a function of, it's an area function. So if you multiply these two, you're going to get something like so look at this chart. You see the area impervious becomes 0.37 multiplied by 15 point something to give you this. Okay, you accumulate the area. Okay, so now this is this. So this becomes 126. Sorry. Before then, let me make it more example. The area, effective area, sorry, let me use the word. Effective area is now area of catchment multiplied by coefficient. Multiplied by coefficient. So in this case, we have this times this. If you multiply the two of them, it will now give you 5.80 meter square. So okay, therefore flow or Q now becomes 5.80 multiplied by the intensity of rain. And what would that give you? That will give you 732.15. 732.15. So from the chart now, we'll read 732.15 against 5%. Okay, this is 732 liters per seconds. Remember, this chart. This is in stormwater, so it has to be huge. It's normally huge. So if you now read this for the stormwater now, if you read 70 this thing against 5%, let's see what it gives us. What it's going to give us. For the chart now, we're not going to use PVC pipe. This is 0.1 mm. So I'm going to close this chart and open the chart for concrete, which is 1.0. Oh, sorry. I want to open it with Adobe. Very important for me. So opening it with Adobe. Look at this place now. You see that the chart is now sorry. The chart is now is now showing you a roughness factor of 1.0, which is for concrete. Okay, so what we got now is 732 against 5%. So this is my 732 here. This is 700 liter per second. This is 800. This is 900. This is 1000. So 732 is just like 700 now. Then I will read it against. Good. I'll read it against 5%. 5 per mil. This thing appears to be too much. Let me decrease to 25%. So 700 against 5. Against 5. Here is giving me 700 mm diameter pipe. 700 mm diameter pipe. 700 mm diameter pipe. So here, the value here is 700 mm. Okay. The chart did not ask you to use anything. So this is 700 mm diameter pipe. That's what I got now by reading against it. So you can see that for the stormwater design, for catchment A, this pipe now, if you're designing for stormwater, the size of pipe is 700 millimeter, which is 0.7 meters. That is 2.5 feet, about that. So gentlemen, can you see the difference? For the sewer, we got 150 mm for the foul sewer line, for the wastewater line. But when it comes to stormwater, we are getting 700 mm. That's to tell you how huge it is. So most times, stormwater can be as much as 90 times, can be up to 90 times the value of sewer. And that's why it is very critical. That's why it can cause flooding sometimes. So the next thing we're going to do is, what is the storm for catchment? There's a chart. Let me see it. Please, if you send me chat and then I didn't respond, maybe that might be the best time. Because I doubt whether I'm sharing the screen. Maybe that's what they're asking me now. Please, I have to leave now. Okay. Okay, somebody has to leave. It's okay. Connection problems. Okay, I think I understand. Just to make sure I'm sharing it. So you see the stormwater now. The sewer line now is giving us 700, while the sewer is giving us 150 and the stormwater is giving us 700. So let's go to number B. So for number B now, for B, this is B. So for B, what is just going to change in B now is simply the area. So the flow now for B, for catchment B, is going to be the area of B. Hold on, stay with me. B is 5.47. So here we say 5.47 multiplied by the peak runoff coefficient. And what would that give us? That will give us 2.03. 2.08. So about 2.08. So here it becomes 2.08 multiplied by 126. Okay. And that will give us okay, this multiplied by this, but that will give us 126 times 126 so that is 2.08 times 126. What do you have there? 262.08. 262.08 liters per second. That becomes the flow for catchment B. But you're not going to abuse this. You therefore say this charge at B will now be 262.08 plus The one for A, 732.15, which is B plus A. So that's the same thing we did last time. And that will give you what? That will give you 988.4. 988.40 liters per seconds. Therefore, size of pipe. What is now the size of pipe? And what is the slope? 3. Okay, are you with me? So if you now go to the chart now, you say 988 is almost like 900 here, against 3, against 3, against 3. So against 3, what are you seeing there? You get something like you get something like 900 mm, no? 800 mm. You get 800 mm. So if you read it, you get 800. So we're going to do the next one now is catchment C. Next one is going to be catchment C. So let's go to catchment C. Catchment C is going to stand alone, just exactly what we are doing last time. What is the area of catchment C? Catchment C is 14.06. So 14.06. So now let me see. You say area of C equals 14.06, but impervious area, which is the real area contributing to runoff, is now this. I don't know if somebody really gets something now out of this. And that will give you 5.22. So the real area is 5.22. Although the actual size of the land is 14 hectares, but the actual area that is a representative of the one contributing to water is 5.22. So you now say 5.22 multiplied by 126. 126 is the rainfall. Is the rainfall intensity of that area. So that will give you what? That will give you 658.93. 658.93 liters per seconds. So for catchment B now, yes, are we in catchment B or catchment C? Sorry, catchment C. Please, pardon me, this catchment C. So to size the pipe now, size it now. Okay, okay. Sorry, I had some distractions. Somebody's chatting me up for something. So you can see for catchment C now, the area is 14 hectare. But the impervious area is 5.22 hectare. So the hectare multiplied by the rainfall intensity per hectare. Remember, that's units. Okay, will now give us 658. Then we'll now go to our chart, check this against this. Chimezie, maybe this is what confused you. This is against, this is 0.3%. But in our chart, you're going to use, let me not confuse people, 3%, which is same thing as 0.3%. Maybe that's what confused you. Okay, I think it's better now. Okay, I'm good to go. So the next one now is catchment D. So catchment D, what's the area? The area is 3.91. Therefore, the impervious area will be 3.91 multiplied by this. And that will give you 1.45. Okay. Therefore, rain intensity will now be 1.45, which is the impervious area. I like you call it impervious area, you call it the paved area. And what would that give you? 1.45 multiplied by 126. 182. Very small area, 182. Therefore, the flow now will now be 182 plus root, sorry. From here, D is B plus C. D is B plus C. Yes, that's the water flowing. We are assuming that water is not flowing out of this place. Water is not flowing out of this place. Water is not flowing out of this place. And the whole water is coming here and going towards here, which is very possible. Okay, outpours, out 4 points in the city are not more than 20 or 10. It's not just everywhere. You can discharge water to the closest stream, but all of them will collect, okay, from Wuse Market to Ibro Hotel, coming down towards Uye, connecting with the one in Jabi, and then from the one from Jabi will connect to Jabi Lake. Okay, the one coming from Udurumi connect to the one in Stadium. You know, there's always interconnection of drains, but that's for another day. So now, what we have here now is that D is actually C plus B. So when we come here, we've gotten our D. So D is 182, and our C is 658. Are you with me? 658. And then B is what? 988. We have it. We got it. You have it. So that value will give you 1,846. 1,846 liters per second. Okay, 1,846. And of course, what's the slope? The slope of D is what? The slope of D is this. So we now say 1846 versus 2.5 in our charts. 1846. I'll go to the chart now. Now, 1846, you'll be wondering, where is 1846? This is 1000. Once it reaches 1000, they no longer write the 2 zeros, they just make it 2. So 1846 will be somewhere here, close to 2000. This is 1500. So 1846 is somewhere here, 18. So I'll read it and I will go up and measure it against 2.5. 2.5 is giving me 110 mm. So 110 mm. That's the size of the, that's 1.1 meter. So for you to know how big it is. So the next thing is catchment. Sorry. So that is it. So the next one we're going to do is catchment E. Sorry, I've not been taking care of the velocity. The velocities are also there. Please, you can do that.
That pipe should be 1,100, sir.
And that's what I did, sir. Look at it.
No,
Okay. So we're on catchment E now. So catchment E will still be the same. What's the area of catchment E? The area of catchment E is 14.84 hectares. So the area equals 14.84. Okay. So the impervious area, which is the real area contributing to runoff, is 14.84 multiplied by the, the runoff coefficient is uniform. In some cases, it might not be uniform. You have to start calculating it differently for the individual plots. So for the runoff coefficient, I want to get the value. So the value will give you for catchment E. Catchment E will give you 695.54. No, the contributing area is 5.51. 5.51 hectares. Okay, of course this one is also hectares. So now 5.51 multiply by what now? The rain intensity, and that will give you 695 liters per seconds. I don't need to go to my charts, gentlemen, unless the slope is different. Since I already have 6.95 somewhere here, I suspect the diameter will just be 800 mm. Well, you can prove me wrong. Somebody, I can check if I'm wrong. That's why in pipe design, sometimes you don't have to do the whole sizing. Once you've done for 10 pipes, like we do in reinforcement, those of you that are civil engineers, if I have a beam that is 4 meters and I have a beam that is 5 meters, if I do a beam of 5 meters and I get my reinforcement size, if I see a beam of 4 meters, I can confidently say a beam of 4 meters can carry the reinforcement of 5 meters. But I cannot say a beam of 5 meters will carry the reinforcement of a beam of 7 meters, because that is not in the direction of safety. So the next one now we're going to do, and this time around, I want everybody to do it. Will be for catchment F. We have done for D. Okay, have we done for D or E? We've done for D, we've done for E. Please, just do for F. What is this pipe size for F? Can we just put our hands on it while I pause the recording? So you now see that for pipe catchment F, this, although the catchment is small, but when you get the discharge, the actual discharge falling on it, or the runoff itself is contributing, is only 219 liters per second. But if you now want to size the pipe passing through it, because it's a collector for pipe D and pipe E, therefore pipe F becomes the 219 of its own catchment plus the catchment of the water coming from catchment B, catchment D, and the water coming from catchment E. So by the time you finish it, you're going to get 26800. You now go to our chart. That was what I was telling us in our chart, in our class yesterday, that the chart has a limit of 1200 mm pipe. When the discharge is more than 1200 mm pipe, you have to use iteration method, you have to use empirical method. Or probably you look for another chart, which I don't have at this point. So beyond 2000, and the slope is about 3%, let's say 3%. So if I read 1800 against 3%, you find out that it's just almost at the border of 1200. Okay? So as an engineer, if you get a flow of say 5 but this also gives you an idea that bigger discharge requires steeper slope. Anyway, we'll still come to that because there's a limit, there's a minimum slope. You can lay a pipe. Not every pipe can be laid in any slope, especially the big pipes. The big pipes cannot be laid in certain slopes. In very small slopes, you don't lay them. It's as good as laying them flat, which of course we lose a lot of head, where head is a requirement. So even if I'm getting something like 4 cubic meter, if the slope is less than 10 per mil, which is 1%, that means this chart will not give you the best accuracy, but it will give you an idea that the member, the cross section, must be more than 1200 mm. So in that case, you're going to use formula, the normal formula, to arrive at that. So the limitation of this training and the limitation of this chart, not this training, but this chart, is that for any discharge that requires a drain size of more than 1.2 mm, this chart might not be strictly applicable. It means you need to combine it, or you need to do some level of iteration to get the value. Okay? So that is that. So what we have done now is how to calculate your so back to our assignment again. What is the pipe size for this and this? So I think we're going to solve that together. So for catchment G, we know that catchment G.
Sorry, could you please take that again? Any drain bigger than 1.2, what did you say?
This chart is not applicable. This chart is not ideal. You're going to use empirical method. You're going to use formula.
Okay.
You're going to do area times velocity. You're going to assume velocity. You know what I mean? You're going to assume velocity and just get the cross-sectional area. And then, you use formula. You use formula to get it. Q equals to AV. So you have your V. You fix your V as 2 meters per second. Okay? Then you now calculate for your A. So when you get your A is the cross-sectional area. So you now know whether you're using a rectangular channel, a trapezoidal channel, or a circular channel. Based on that, you now use the appropriate geometric formula to get it. But this pipe size saves you time. This chart saves you time. Once you get your discharge, you just go to the chart, you read it off. If somebody uses formula, you end up where you're ending. So with this chart, you can design for 1,000 pipes in 2 days. But somebody that uses formula, I mean, that would be daunting, I would say. So let's quickly use 5 minutes and do these assignments and know that I'll save the video. It becomes a video for Stormwater. Okay, someone has a question, go ahead. So now for catchment G now, what is the size of this? So for catchment G, we simply look at what G is. G is 14.06. Okay, 14.06. Am I right? So 14.06 is the area. So the true impervious area will now be multiplied by 0.37. Multiply by 0.37, and that will give you.
Please share the screen.
Okay, sir. Okay, sir. So so 5.22. So that will give you 5.22. Therefore, the intensity 5.22 multiplied by the rain intensity, whatever you get the rain intensity, and that will give you 126 multiplied by 5.22. That will give you 657. 657 liters per seconds. So the slope of G is still 3. So I'll go to my chart now. 657 is almost like 700 against 3%. It's giving me 800. Common sense will tell me that thing should be 800. Why? Merely looking at the chart, the layout, can't you see that G is almost the same as C, almost the same thing as A, almost the same thing as E. Then that A is bigger. That's why A was giving us 900 mm. Why G is giving us 800 mm. So the final one now is H. So H will now be F. They have to calculate H. Okay, it has a small catchment. H will now be itself plus G plus F. So for H now, what do we get now? For H, we'll simply say, what's the area of H? H is 2.34 hectares multiplied by the coefficient. That will give you 0.87. 0.87 hectares is the contributing hectare. So 0.8 multiplied by 6. .87 multiplied by 126. That will give us another 126. So 126 liters per second. Very small inflow. Very small inflow. But the flow now in G will now be 126 plus the value for F and the plus the value for G, which is 657 plus the value for F, which is 26800. 26800, and that will give you 3,393. All right, 3,388. 3,388 liters per seconds. Remember, I'm not adding the velocity. You can just read, as you're reading out the chart, you're also reading out the velocity. So 3,388 against the slope. What's the slope again? Slope is I think it has a gentle slope. The slope is 2% or thereabout. So here we easily go here and you see that this is 3. The minimum slope I can calculate for this is 5%. So if I'm talking about 2%, is somewhere here. There's no value for it. So this is now where you use formula to get it. So if you are getting it, for me, if you ask me, using my experience and idea, I'll tell you that this pipe is about 1,500 mm. If you use formula, unfortunately, I can't prove it now. So H. So if you now do 3388 versus 5%, which is not what the slope is, but the slope of 2% is approximately 1.4 meters to 1.5 meters pipe. 1.4 to about 1.5 meter pipe. The charts, or let's just say, not applicable to charts, but use empirical method. Use empirical method. Are we together? You know how I got this? If I assume my velocity is 2, if I assume my velocity of 2, that's what we normally assume. This is assumption. Assuming, I'm just assuming. Therefore, A Q is equal to AV is equal to 3388 is equal to A times 2. Therefore, A is equal to something around 1.6, I think so. This is empirical. This is a lazy man's work. Okay, this is a lazy man's work. It's a lazy man's work, but you have to do it. You need to fix that velocity well. You need to fix it. So you need to calculate the slope well. You need to fix the velocity well. Justify your velocity. So please, this should be off record. Assumption. So this is how you calculate this, given this, and you are asked to do the stormwater design. You can see that the same formula we use for the seawall design is the same formula we use for the stormwater design. The difference being that the parameters, the input parameters are different. While we use hydrology for stormwater, we are using wastewater flow for sewer. So if you are asked to do this design, this is exactly what is expected of you to do.